Hi everyone! In this section we're going to look at one of my favorite topics, which is the dynamics of uniform circular motion. We've mentioned before that as an object is moving in uniform circular motion, it moves at a constant speed, but it's accelerating because the direction of its velocity vector is constantly changing. And this means that it has an acceleration that's directed towards the center of the circle. Because of this, it's helpful to use a new coordinate system like we did with objects moving along an incline. So the coordinate system that we'll use here is that the x direction is the radial direction. So if we consider an object like this moving in the circle, the x or the radial direction points towards the center of the circle. That's the positive x direction at any point. So in this sense, the coordinate system rotates with the object, and it doesn't matter at which point in the circle it's moving, we can analyze its forces in the same way. Then the other direction, the y direction, if you want to call it that, is the tangential direction, which is perpendicular to this radial direction. This is really useful because then the net force in the x direction is equal to max, where the acceleration is, and then the net force in the y direction is equal to 0 since it's not accelerating in that direction. So as we've seen, the net force for an object moving in uniform circular motion is directed towards the center of the circle, which is in the positive radial direction. I've called this the x direction, so we have the net force in that direction equal to mac, which is the centripetal acceleration that we saw in the last section. So we can plug in the expression for that, and we have the net force equal to mv squared over r. Sometimes you might see this called the centripetal force. I don't like to use that term because this isn't a new force. This is just the net force that's directed towards the center of the circle, and it's caused by forces that we've seen before, such as gravity, the normal force, tension, and friction. And in the next examples, we'll look at how each of these forces can be involved in uniform circular motion. Example 5, an energetic father ties a 2-meter long rope to his 30-kilogram son and whirls him around on frictionless ice in circular motion. A. Draw a free body diagram showing the forces on the child. B. How fast is the child moving if the tension in the rope is 100 newtons? C. How many revolutions per minute does the boy make? D. What happens to the boy if the father lets go? Alright, so for A, it looks like this, and then the child is this box that will then be moved in a circle. So towards the center of the circle is the force of tension, Ft. Then there's also the normal force and gravity. We can ignore friction this time since it says frictionless ice. And these are in the perpendicular direction. We can call that the y direction if we want, and that's 0. It is accelerating, however, in the x direction, which is the radial direction, where we'll have our net force equal to mac. We'll need that for part B, which asks how fast is the child moving. So in this x direction for part B, we have Ft equals mac, since tension is in the positive direction towards the center of the circle. So then Ft equals mv squared over r, which means v equals rft over m, the root of that. So v is equal to the root of r, which is 2 meters. It's a 2-meter long rope, and the father is standing in the center of the circle, so that's the radius, times the tension, 100 newtons, over 30 kilograms, which gives 2.58 meters per second. All right, now for C. How many revolutions per minute does the boy make? So what is the frequency in RPM? We know that V equals 2 pi RF. So the frequency is V over 2 pi R, and this will give us hertz. So 2.58 meters per second over 2 pi times 2 meters is 0.205 hertz. We need to just do a conversion to get this to RPM. So 0.205 revolutions, essentially, per second, times, we have 60 seconds in 1 minute. So multiplying by 60 is 12.3 revolutions per minute, or RPM. Now part D is what happens to the boy if the father lets go. So let's look at our diagram here. What would happen when this string breaks is that the child would move off tangent to the circle. So the child is going to continue moving in the direction they were moving, maybe that way, depending where they were at that point. I'll draw it down here now. So if they're moving in this circle, let's say they're at this point, then they would continue moving off tangent to the circle. And this is due to inertia. So we can write that the child would move away tangent to the circle. And this is Newton's first law, which is inertia, that says that now there's no longer a net force that's holding that object in the circle, causing it to accelerate in the circle. And in the absence of that, it will continue as it was moving, which is in this direction at any point. At any point, the object is moving tangent to the circle. Example 6, a 200-gram block on a 50-centimeter long string swings in a circle on a horizontal frictionless table at 75 RPM. A, what is the speed of the block? B, what is the tension in the string? Okay, so the block, it looks similar to the last problem, is moving in a circle where tension is towards the center of the circle and providing the net force for uniform circular motion this time. Fn and Fg are in this other perpendicular dimension, and the net force in that dimension is equal to 0. So the net force in our radial direction is MAC, which is just Ft, which is equal to mv squared over r. So we're going to use this, but for part A, it just asks what is the speed of the block, and since we're given the frequency, we can find it. We have a frequency of 75 RPM, revolutions per minute. So let's convert that into hertz, revolutions per second. So times 1 minute over 60 seconds is 1.25 hertz. And then we know that V equals 2 pi RF. So the speed is 2 pi times 0.5 meters, 50 centimeters, times 1.25 hertz. And this gives 3.92 meters per second for the speed of the block. Okay, now what is the tension in the string? So back to this, from our net force equations, we know that the tension is the net force for circular motion, so mv squared over r. And now we have all of those variables that we can plug in. So Ft equals mv squared over r, which is m.2 kilograms times 3.92 meters per second squared over r, 0.50 meters, which gives a tension of 6.15 newtons. Example 7, the conical pendulum. A 1.5 kilogram ball is swung around on a 1.8 meter long rope that makes an angle of 40 degrees to the vertical at the top of the pole. Determine the tension in the string and the speed at which the ball moves around the circle. Okay, so the free body diagram looks like this. We have tension at this angle of 40 degrees. I can move that angle here because these are both vertical lines, so we have one line intersecting two parallel lines, so the angle has to be the same, or it's the Z rule you might have learned in math. So that's 40 degrees. Alternatively, you could use this angle by doing 90 minus 40 since it's a right triangle. Then we have the weight downwards, and we will need the radius. We're given the length of the string here at 40 degrees, so let's find that first. I'll have r equals 1.8 meters sine 40 since it's the opposite side to this angle, and that's 1.15 meters for the radius of the motion. Okay, now we're looking for the tension in the string and the speed. So for the tension, let's try using the y direction. The net force in this y direction or perpendicular direction here equals 0. So we have Fty minus Fg equals 0. So this is cosine of 40 because it's adjacent to the 40. So Ft cos 40 minus Fg equals 0. Ft equals Fg over cos 40. So this will be 1.5 kilograms times 9.8 newtons per kilogram over cos 40, which is 19.2 newtons. Now with that tension, we can look in the x direction and find the speed. So in the x direction, that's equal to MAC. So we have the only force in the x direction is the horizontal component of tension, just going back up here. It's this component which is sine since it's opposite to the angle. So that's going to be Ft sine 40 equals MAC, which is mv squared over r, so we can plug in for the centripetal acceleration here. And then solving for the speed, I have v squared equals r Ft sine 40 over m. So then v equals the root of 1.15 meters. Ft was 19.2 newtons. Sine 40 divided by 1.5 kilograms, which is the mass, and this gives a speed of 3.08 meters per second. Example 8, a sports car of mass 950 kilograms crosses the rounded top of a hill, r equals 75 meters at 22 meters per second. It then travels along flat ground and then into a dip having the same radius. A, calculate the normal force on the car at the crest of the hill, on flat ground, and at the bottom of the hill. B, calculate how fast the car needs to go to get air right at the top of the hill. Okay, so the free body diagram looks the same in each of these three cases. At the top of the hill, on the flat surface, and then in the dip here. What changes is the direction of the acceleration and the positive direction of motion. So the easiest case is this one, I'll call it 1, when the object's moving on flat ground at a constant speed. In that case, the net force is equal to 0, so we have Fn equals Fg. And let's calculate that. It's mg, which will be 950 kilograms times 9.8 newtons per kilogram, which gives 9,310 newtons. Okay, now if we look at the top of the hill, let's call that part 2. The direction of positive motion is towards the center of the circle, which is down in this case. So our net force in that radial direction is equal to MAC, which is going to be Fg, which is in the positive direction now, minus Fn. And then we're solving for the normal force. So I'll have Fn equals Fg minus MAC, or Fg minus mv squared over r. So this is going to be 9,310 newtons minus 950 kilograms, 22 meters per second squared over 0.75 meters, which is 3,179 newtons. Okay, let's do the last one and then I'll talk about what this means. So number 3, when the car goes through the dip of the same radius, now the positive direction is up because up is the direction towards the center of the circle. So we'll have the normal force minus Fg when we go to write the net force. All right, so part 3, the net force in the radial direction is MAC. So I have Fn minus Fg equals MAC, or Fn equals Fg plus mv squared over r. So this is going to be 9,310 newtons plus 950 kilograms times 22 meters per second squared, over 0.75 meters, which gives 15,441 newtons. So this is really interesting. We can see that the normal force is equal to the weight as expected on flat ground. When it's moving over the hill, the normal force is less than the weight, and then in the dip, the normal force is larger than the weight. You might have felt this before. If you go over a hill or through a dip of a small radius, you can feel kind of something change in your stomach. What you're feeling is the difference in the normal force, which is the apparent weight. So you're really feeling a difference in the apparent weight as you go over a tight curve. Part B asks how fast you have to go to just get air at the top of the hill. So this means just lift off the ground at the top of the hill. So this was our diagram from before. If you're just lifting off the ground, you're no longer in contact with the surface, so the normal force goes to 0. So that means just momentarily you're still in uniform circular motion, but only the weight is acting on the car or the object. So we'll have the net force equal to MAC, which equals FG. So MV squared over R equals MG. And notice that the mass cancels, and the speed is V equals the root of GR. So it's a nice short expression we get here. 9.8 meters per second squared times 75 meters, which is 27.1 meters per second. Example 9, a roller coaster travels along a vertical loop of radius 7.4 meters. At what minimum speed must the coaster be traveling so that the passengers do not require restraints to avoid falling out at the top of the loop? All right, so let's look here. If the passengers are going on this loop, so they're upside down here, then the normal force would be coming out from the surface, so towards the center of the circle, which is the positive direction, in the same direction as FG. So just looking at this, if we write our net force equation equals MAC, in the radial direction, I have Fn plus Fg equals mv squared over r. So we don't know what this normal force is. It depends on the speed in a way. They're related. But we can see that for the minimum speed to occur, we want the minimum. This will occur when Fn equals 0. So this is essentially when the cart of the roller coaster, or when the people in the cart, just slightly lift off the ground so that there's no normal force from the surface. So that's 0 to get the minimum speed. It can go faster with no problem and make it around the loop. So this is 0, so we have Fg equals mv squared over r. So mg equals mv squared over r. And again, we have v equals the root of gr. So this will be the root of 9.8 meters per second squared times 7.4 meters, which is 8.5 meters per second as the minimum speed for those passengers to be safe. Now this is without restraints. If we had restraints, they could pull the passengers up into the cart this way and keep the cart on the track, of course. So we could have negative for Fn. In that case, we could get a lower speed if there were restraints. I mean, even 0, right? We would expect the cart to still be safe at the top if it were to pause at that moment for a real roller coaster. Example 10, in a rotor ride at a carnival, people say that they were pressed up against the wall. The radius of the ride is 4.6 meters and the rotation frequency is 0.50 revolutions per second. What is the minimum coefficient of static friction so that the riders don't slip? I don't know if you've been on a ride like this before, but basically it's a cylinder that spins, and as it spins, when it's fast enough, the normal force can provide a net force to keep the objects in circular motion, and they can actually stick to the wall due to the relationship between the normal force and static friction. So you could lift up your feet and then stick against the wall once it's moving fast enough. So in that case, we would have static friction going up, keeping the person against the wall, or up against the wall, and then the weight down. and the normal force comes outwards from the wall here, which provides the net force for circular motion. So in that y direction where we have static friction, that will be equal to 0 since the person is at rest in that direction. So static friction equals Fg. Now, because we're looking for the minimum coefficient of static friction so that the riders don't slip, we're going to want to take the maximum value of static friction at that coefficient. So if you think of the coefficient of a range of the coefficient of giving a range of possible static friction values, we'll take the maximum of the range so we can get the lowest possible friction value, coefficient of friction value. Okay, so we have mu s Fn equals mg from this equation. Now let's look in the x direction. In the x direction, or the radial direction, we have the net force equal to mac. So Fn equals mv squared over r. Now before we continue, we'll need the speed, so let's find that. V equals 2 pi rf. So 2 pi times 4.6 meters times 0.5 hertz, which is 14.5 meters per second for the speed. So now let's plug in this expression for the normal force here into our y equation. So mu s, instead of Fn, I'm writing mv squared over r equals mg. Now the mass cancels, and I end up with mu s equals rg over v squared. So that's going to be 9.8, this is g, meters per second squared, times 4.6 meters, the radius, over 14.5 meters per second squared, which is 0.214 for the coefficient of static friction. An unbanked curve in physics just means a flat curve, so it's not on an incline. And in this case, the force of friction is the net force towards the center of the circle that is responsible for turning the car in uniform circular motion. So it's actually impossible to turn the car without friction, or to drive the car for that matter. But if you think about turning on ice, it's much more difficult when the friction is low than on a regular ground outside where the friction is higher. Something else to note is that the net force towards the center of the circle, if this is the car and it's going to drive around this circle, the net force is static friction. This is because though the car is moving and maybe is experiencing, well, definitely is experiencing kinetic friction in the tangential direction, there's static friction in the radial direction since it does not move radially. It remains at the same radial position, the same distance to the center of the circle the entire time. So it's actually static friction that's toward the center of the circle. Then in this vertical direction, we have the normal force and the force of gravity, which are balanced. The third dimension is what we're not drawing, which is where there would be an applied force from the motor of the car and friction and maybe other forces, but that must be balanced in order for the car to move in uniform circular motion. Example 11, a 3,000 kilogram car rounds a curve of radius 50 meters at 30 kilometers per hour. The coefficients of static and kinetic friction between the car's tires and the road are 0.90 and 0.75 respectively. A, which type of friction acts in the radial direction? B, can the car make it around the corner without slipping? And C, what is the maximum speed at which the car could take the corner without slipping? Okay, for any unbanked curve problems, the diagram will look like this. So I've just added example 11 onto my free body diagram from before. And so the first question is what friction or what force acts in the radial direction? And we know that this is static friction. Static friction between the tires and the road because they're not moving in that radial direction. All right, now for part B, we want to know if the car can make it around the circle without slipping. So let's find the maximum value of static friction that's available for this coefficient. So that's mu s Fn. Again, because these forces are balanced in the y direction, we have Fn equals Fg. So this is mu s mg, which is 0.90, the coefficient of static friction, times 3,000 kilograms, times 9.8 newtons per kilogram. So 26,460 newtons for the maximum value of static friction. So that's how much static friction is available to turn the car. What's required is the net force must equal mac in order for it to make the turn in circular motion. So mv squared over r, and we have the mass, 3,000 kilograms, times the speed, 8.33 meters per second, which is 30 kilometers per hour, converted to meters per second, squared over 50 meters, gives 4,163 newtons. So that's much less than required. So since this maximum static friction value is greater than the net force required, we know that yes, the car will make the turn. So then following that, the question is, well, how fast could it go and still make the turn? And in that case, we would have our net force equal to the maximum value of static friction, Fs max. And then that's going to equal mv squared over r. So we'll get v squared equals r Fs max over m. So v will be the root of 50 meters times the maximum force we found, 26,460 newtons, divided by 3,000 kilograms, which gives 21 meters per second, and that's about 76 kilometers per hour. And that's the maximum speed that it could make it without slipping. Example 12, a car travels at a constant speed of 13.4 meters per second on a level circular bend in the road. What is the minimum coefficient of static friction such that the car just makes the bend? So similar question to before, but now we want to find the minimum coefficient so that the car can make the bend. Again, if you think of the coefficient as providing a range of possible static friction values, we're going to want the maximum static friction at that coefficient. So Fs max equals mu s Fn. And we have the same free body diagram here. Static friction towards the center of the circle in the positive direction, Fn up and Fg down. And then in the y direction, there's only the normal force and gravity and they're balanced. So we have Fn equal to Fg, which is mg again. Okay, so in the radial direction, we have the net force equal to mac, which is going to be Fs max. So mv squared over r equals mu s Fn, or mv squared over r equals mu s mg. And we notice that the mass cancels again, so I have mu s equals v squared over gr. And then we can just plug that in. So 13.4 meters per second squared over 9.8 meters per second squared times 50 meters, which is 0.366 for the minimum coefficient of static friction that will still allow the car to make the turn.